All right, I think we will get started. So remember homework 5 is due next Tuesday. Okay, so that's and then 6 is due after 1 week after that, and then we'll have exam in the week, the Friday that week. Um, for in-seat is today's classroom in disinfection. I assigned to Turing and Jalen. Okay. Um, Today we'll be looking at chapter 20. So we'll be looking at electric current, resistance, and Ohm's law. Okay. So let's take a look here. So first, let's take a look on the definition for electric current. So electric current is defined as the amount of charge going through a certain area over time t. So it's delta q over delta t. Okay. So the area doesn't really matter. You can have a small area, larger area. Okay. So it's not relevant to the area, but that's the passage point. Okay, of the current. The SI unit for current is coulombs per second. Coulomb comes from Q charge, and second comes from time t. Or it's equivalent to ampere. Use symbol A for it. Okay, so it's C over S, which is equivalent to A. All right. So when you have a current going through a conductor, now it depends on materials. For some material, the carrier for the current is positive charge. Other materials will have negative charge. Okay, so for most metal conductors, the carrier is the electron, so it's negative charge. For some semiconductors, you will have positive charge carrier. Okay, as the way that charge is moving. So it depends on material, but for most metals, it's electron. The current should be in the same direction as the electric field. So if you have positive charge carriers, then those two are in the same direction. The carrier and the electric current, electric field are going in the same direction. Okay. If you have negative charge carriers like electrons, then the electron moves in the opposite direction of the electric field and the electric current. So if you have electrons they are moving in to the right, left, then the current is to the right. Okay. So just keep in mind that for electrons as carriers, that's in the opposite direction. Motion of electrons are in the opposite direction of the current and electric field. Okay, so we'll take a look on a simple example here on how to calculate the current, or actually given current in this case. You're looking for how much charge flows through the light bulb. Okay. All right. So this one says you have a flashlight bulb that carries current of 0.38. All right, so it gives you the current as 0.38. That's in amperes for 98 seconds. So T is 98 seconds. So I is equal to 0.38 amps, and then T or delta T is 98 seconds. Okay, so according to the definition, I equals to Q or delta Q over delta T. It asks you to find delta Q. All right, so then delta Q should be equal to I times delta T. All right, 0.38 amps times the 98 seconds. Okay, that will give you how much charge is going through the light bulb in that given time period. Okay, so it will be roughly, this is 37.24 in coulombs. Okay, If you want to keep 2 sig figs, then just 37 coulombs for that first question. For the second question, is asking how many electrons flow through the light bulb in this time. Okay, so pretty much if you have a light bulb, the conductor here will be the metal, so then the electrons are the carrier. Okay, so you're looking for a number of electrons. That should be equal to the total charge that flows through divided by the charge of the electron. Okay, so I'm going to use E for the charge of each electron. So you are doing 37.24 coulombs divided by 1.6 times 10 to the negative 19 coulombs. Okay, each electron carries that much of charge, but negative. Okay, so we are looking for the amount, the number of electrons. Okay, so you can take the absolute value of that because this is in absolute value, the positive value there. Okay, so that will give you 2.3 times 10 to the 20 electrons. Okay. So that many electrons flow through the light bulb in this time. Okay. All right. So I think this one is kind of straightforward, but let me know if you have any questions about it. Okay. All right. um, so when you turn on the light, or the light switch, so the moment that is on, turn on, flip to on, you'll see the light will come out from the light bulb, right? So it happens like kind of instantly. But so actually, the moment you turn on the switch, so then the electrons start to flow in through the switch at that moment, okay? But the electrons that go into the switch, actually, they do not come out immediately. So it's kind of like if you have 2 electrons comes in on one end, then 2 has to come out, okay? So these 2, the ones that actually moves in here actually moves rather slowly and then it appears, okay? In reality, when an electron enters a conductor on one end, it has to go to this zigzag path. It sometimes comes back because it bumps into atoms or electrons, okay? So that's the more likely the pathway. It's not like straightforward, going straightforward. It will bounce back and forth or maybe onto the sideways. So the motion of electrons actually, it's rather bumpy. And so the speed that electron goes on average is called a drift speed, okay? So that's refers to here, if you measure the distance it travel in given time t, then divide by t will give you this v, the actual velocity vd, okay? It's rather a small velocity than it appears. From this chapter on, we are going to take a look some of the circuits, or in reality, this is what it looked like, okay? But when we are doing schematic drawing, then you will see something like this. So when you see a longer line that is close to a short line that represents the battery, okay? In reality, this might be a battery, one form of the battery. And then the light bulb is pretty much represented by a resistor. Okay, so on the zigzag line like that. Okay, so that represents this physical picture here for this drawing over here. All right. The current will flow from the positive terminal through this light bulb and then comes back to the negative terminal. Okay. In some textbook, okay, so the resistor, so pretty much you can treat the light bulb as a resistor. So this is also like the symbol for resistor. So some textbook use just the rectangular box for a resistor. So you might see in some cases, so this can be drawn as like positive and negative here, but instead of having zigzag line, you might see just a rectangular box. Okay, so that also stands for a resistor. Okay. All right, so that might be just another area of representation for resistor. Okay. And we'll be checking on other elements later on, just maybe when as we encounter them. Okay. For the charge carriers to go through a conductor, so it's similar to like the gas molecular movement that we mentioned earlier. So you can calculate, okay, the amount of charge. Okay, so that should be equal to small q is the charge for each of the charge carrier. It could be an electron, it could be a positive charge, times this n. Small n is the number of charges per unit volume. So this is like number density of the charge carriers, times A, which is the cross-sectional area of the conductor, this guy here. And Vd is the drift velocity of the charge carrier, okay? Times delta T in a given time period, okay? So this is number of like the number density, A times Vd, that gives you the length of the cylinder that the charge goes through or in given time. And then area times this. So this gives the volume of this cylinder, okay? So number density times volume gives the total number. So m times AV delta T is the total number of the charges times the charge of each charge. That gives you the charge flow through the given time period, okay? According to current definition, so total charge over delta T, so then you get rid of T. So in this case, you can see the current, it's not determined by the time, okay? It's rather determined by the number density of the charge carrier, and then the charge of each charge carrier times area times the drift velocity, okay, Vd, all right? In the original definition, we see there's no relevant, it's not relevant to the cross-sectional area, but in this, if you look into detail here, you'll see that it actually does depends on the area, okay? If you have a larger area, you'll expect to have a larger current going through, okay? All right, or if you look at the charge current density, then you do the current divided by area, okay? So then that's not relevant to the cross-sectional area, but it's pretty much defined by these three quantities, which is material dependence, okay? So for the same materials, you'll get the same current density. For example, if you have a copper wire, then the current density should be the same, no matter if you have a thinner wire or thicker wire, okay? All right. So that's on current density there. Next section here, or let me pause to see if you guys have any questions on the first section on current. All right. So if not, then move on to next section, talks about Ohm's law. So for the current in the conductor also depends on the voltage. All right, so this is one way of writing Ohm's law. So R equals to V divided by I, okay? So, or you can write like I equals to V divided by R, okay? So that tells you that current is depends on the voltage you apply across the conductor and then the resistance of it, okay? So either way, so resistance here is the in ohms, okay? In the unit of ohms is voltage over amps, okay? So it's 1 V over A equivalent to ohms. Okay, so that's basically Ohm's law gives the relationship between V and then I and R. Okay. Some of you guys did lab on Wednesday on Ohm's law, but the rest of you guys will be doing this today. All right. All right. Now, just keep take one more note here that Ohm's law is not a universal law. Okay, it's only useful for certain materials. Okay, mostly the metallic conductors. All right. But in this class, if not otherwise specified, then all conductors are assumed to be like metals, and then they will obey Ohm's law. Okay, unless if in other contexts when you guys are encountering say semiconductor, then that doesn't apply here. Okay, Ohm's law doesn't apply here, or maybe superconductor, it doesn't apply there either. Okay. All right. Now, the next section is more related to Ohm's law. So basically, what will be the resistance of a conductor? Okay, so it's determined by the material. Okay, so each material will have its own resistivity. All right, then given the dimension of it, and then along with the resistivity, you can calculate the resistance of a conductor. Okay, so it's given by this equation. So the resistance is proportional to resistivity rho here. Okay, so I think earlier when we saw rho, it stands for density, but in this context, it stands for resistivity of the material, and then times the length divided by the area. Okay, so if you have longer wire, then the resistance will be larger. If you have thinner wire, then the resistance will be larger too. Okay, and then if you have thicker wire, resistance will be smaller. Okay, so that's something you can think about, like for highways, if you have more lanes, then the traffic will be smaller, less than if you have like just a couple lanes. Okay, so that's like traffic density as well. All right, so this one will give you how to calculate the resistance of a resistor of a certain conductor. All right, so resistivity is material specific. So you can see for different materials, for conductors, the resistivities are small, so they are 10 to the minus 8 orders. For insulators, resistance is very high, okay, more than 10 to the 9, sometimes 10 to the 17 order, okay. And for semiconductors, it's in between, okay. All right. So again, look up this table. Let's take a look on one example here. It says a current of 0.83 or 0.86 amps flows through a copper wire, 0.74 millimeter in diameter when it's connected to a potential difference of 15 volts. How long is the wire? Okay, so you are given a wire. You are given a copper wire. All right. So for a copper wire, you can look it up in the table, the previous table here. Let's take a look for copper wire. So there are two types of copper wires. We are going to just take this one because it didn't specify it's an annealed one. So this one is then 1.68. Okay, so you can take down the row number, the resistivity of copper, 1.68 times 10 to the minus 8 ohms times meters. Okay. And then it tells us the current going through it is 0.86 amps. It tells you the diameter of it. So this guy's the diameter is equal to 0.74 millimeter. it tells you the voltage applied is 15 volts. Okay, so V is equal to 15 volts when you apply that onto this wire. Now it's asking you what will be the length of this wire. You're looking for L. All right. So for its resistance, this is the equation: rho times L divided by area. Okay. Now for a wire, it's a cylinder, right? It's kind of cylinder, thin cylinder. So the area is equal to, if you are given diameter, then that's pi over 4 times diameter square. Okay. And you also need Ohm's law here. I is equal to V divided by I. Okay. And then you are looking for L. All right, I think I can have you guys work on this, and then we can take a look at the solution together after that. All right, so let's take a look here. So you're looking for L, right? So you can check, and then you probably will find this equation contains L here. So to solve for L from here, you need to know A. So A you can calculate it. Okay, so because it gives you D, so you can calculate A. The rho that you have it. Okay. Now R, you need to know R. Okay, so you don't have R. So now the question is, can you find R? Okay. So let's also other information that we haven't used. We know that V is equal to 15. We know I is equal to 0.86. Okay, so you can solve for R from here. So once R is solved, then L can be solved. Okay, so you can calculate R, calculate A, and then put those two into this equation to solve for L. Okay. So you can do that. You can do like R equals to 15 volts divided by 0.86 amps. That gives you resistance. You can calculate A equals to pi over 4 times D 0.74. Now just pay attention here. This is in millimeter here. So times 10 to the minus 3 that in meters. Okay. And then do not forget to square it. Okay. And then you can have your A there. Then you can calculate your L. So from there, L is equal to, you'll have to move this guy to the other side. So A times R, okay, divide by rho, okay. So I did this first, then I put pi over 4 D squared as my A. My R, I did V over I, okay. I did V over I and then divide by rho. That's usually what I like to do. I just plug in the numbers at the end here. Squared, okay, times 15 over 0.86 amps divided by this 1.68 times 10 to the minus 8 in ohms times meters. All right. So if you have everything correctly plugged in, you'll get about 4.5 times 10 to the second. So 450 meters, okay, for the length. Any questions you guys might have on this? All right. Right. So if not, so to summarize, resistance of materials, they typically go up as temperature goes up, because then movement of the atoms inside the material actually is much more intense. So then the charge carriers will bump into more atoms in less sense. So that's purely due to thermal effect. Okay. Yeah, and then this effect, this property can be used as thermometers. That's the one we saw when we were doing expansion of material. So actually, it's For the thermistor is the conductor. So as temperature goes up, the resistance. Oh, actually, that's the other way around. That's no thermistor. They are not. Sorry, my bad. They are not. Okay, they are actually not conductors. They are rather pretty much like semiconductors. All right, and resistivities decrease as temperature goes down. All right. There are another type of material called superconductor. When the temperature drops to certain threshold, then suddenly the resistivity goes away. It drops to 0. Okay, and that temperature is called critical temperature of that. It's TC. All right. All right. So this is how you can use the resistivities and then its temperature dependence to use it as a thermistor. Okay. So as temperature goes up, the resistivity goes up. Okay. In general. All right. So for different labels, we are using, so like olden days, we are using like those types of labels. Now these days, we are pretty much using more the energy efficiency one. So um, so what's the power being consumed by those different types of labels or resistors? Okay, so you can see the power is equal to energy divided by time. T, U stands for energy, T is the time. All right, so U is equal to in electricity here, it's the charge times the voltage, okay, times the potential. That's what we learned in the previous chapter. So U equals to that. So then power can be rewritten as Q times V divided by T. Now, we just learned that if you do Q, the charge over time T, that gives you the current, right? So then power is equal to the current times the voltage, I times V, okay? That gives you electrical power, all right? So if you know the current going through and then the voltage across it, then you can calculate how much power it consumes, okay? Power should be in the units of watts, the SI unit of watts. So P equals to I times V or V times I, either way. Now, according to Ohm's law, if the material obeys Ohm's law, then you can write power in two other expressions. Okay, so power is I times V. Now, according to Ohm's law, V is equal to I times R. All right. So then power is equal to I squared over times R. Or in the other way around, you can write I as V over R according to Ohm's law. Okay, Ohm's law basically says R is equal to V over I. Then you can rewrite I or V from Ohm's law. So then power is equal to V squared over R. Okay, so if you know the current, you know the resistance, you can calculate what's the power. So I squared times R. Or if you know voltage across the resistor and then the resistance of it, you can calculate power by V squared over R. The power consumed by a resistor pretty much becomes heat. Okay. All right. So with power, let's take a look. This example, it says a 65 volts generator supplies 4.8 kilowatts of power. How much current does the generator produce? So it gives you the voltage, it gives you the power, it's asking you the current. So for power, it could be I times V. It could be I squared times R. It could be V squared over R. Okay, so those three expressions. Now in the problem, it tells you P, it tells you V. It's looking for I. So you pretty much will just use the first equation, right, for that. You'll be using the first equation. So in that sense, I think we can take a look here now together. So I then should be equal to P over V, okay, power divided by the voltage. The power is, it says 4.8 now kilo ohms, so that means times 10 to the 3, okay? And then divided by 65 volts, that will give you 74 amps for the current, all right? Just remember to convert kilowatts to watts, okay? Times 10 to the third. All right. Next, we'll take a look on the electric hazards and our human body. Okay, so I don't know if you guys have ever been or ever got electric shock, but I had one very unpleasant experience when I was very little. I don't remember. Maybe I was 4 years old or 5 years old, but I put a metal push pin into one of the power outlet, and then it was like, wow. Yeah, I don't know how I survived, but I'm here. So, yeah, that's one of my early memories that I could recall. All right, but basically, it could be very dangerous when you are dealing with electricity. Okay, so there are two main hazards. One is called thermal hazards. So if you see like fire being set up by electricity, so that's pretty much the thermal hazards. Okay, the other one is the shock hazards, that when an electric current passes through your body. Okay, so we'll take a look at those two one by one here. So when a thermal hazardous happens, that's pretty much because so in the wire, so typically in one wire that you see, so it's wrapped by insulators, but in between, typically there are two metal wires. They are also insulated by insulators. Okay. Now as time goes, so the insulation may warm out. So then the two metals will be might have chance to be like in direct contact. Okay, so in that case, now usually when an appliance would have a rather large resistance inside it. Okay, so then for the voltage supply in here, we are having 120 volts over a very large R, then the current going through the wires will be small. Okay, now, in the case that the insulation is warm out, so if the two wires are direct in contact, so then the current will go through this direct contact point rather than going through the appliance, okay? Because current is kind of like lazy. It wants to go like shortcut over here. If it's small resistance, you prefer go that way, okay? Not going that way. So then for the given like 112 volts over this very small resistance in typically like in the tens of ohms, so like 0.1 ohms. You can imagine that then there will be 1200 amps of current going through here. All right. So then V times I in that case will give you like 144,000 watts. Okay, that's a huge power there, which will heat up the materials pretty quickly. Okay, remember the power consumed by a conductor becomes the heat inside it. So then temperature of this will rise up very quickly. All right, then it will set fire of the material. Okay, so they're causing fire there. All right, now there's something we can do to prevent that from happening. So like um, electric breaker, something like this. You can, or you can put a fuse. All right, which when the temperature goes on, when the current going through here is very large, then temperature here will also increase. Now the fuse are very easily melted. Okay, as once the temperature goes up, then it will melt it. Okay, so then we'll cut off this power supply. Or you can have a breaker box like this. Okay, now the one on the wall in the classroom over there, that's a electric breaker. So the mechanism is here. When you have current, large current going through here, then this is metallic strip. Okay, so then it will bend because temperature here will goes up. Now the two materials respond to temperature change differently. That means they expand differently. So then it will go bend this way. The temperature goes up, it will bend this way. All right, then this one will drop off. All right, it will cut the power in that sense. Okay, so this goes down, then the switch level will be cut off. Right, so there are two ways to prevent thermal hazardous there. All right, the shock hazardous is when the electricity goes through your body. Then actually, when that happens, all right, then yeah, it gives you a very unpleasant feeling over there. If it's not too big, but then it could be very dangerous. Okay, when it's too big. So in the labs, we try to reduce shock hazards. So we are using batteries. They are only 6 volts. Okay, for many cases. So that's safe. So as long as the voltage is like less than 30, 36, then you are safe. Okay. So all right. So when the current going through your body is too big, then you cannot let go. Okay, so that's that curve says there. So we'll take a look on one example here. This is associated with thermal hazards. So let's take a look at real numbers to see how much or what would be the temperature for a particular cases here. So when a short circuit happens to a 120 volts appliance that has a 0.500 ohms resistance, okay, or the appliance cord, actually the wire, not the appliance itself. So when that happens, the two wires are in direct contact and it's having only a very small resistance. So then the electricity goes through the wire from one wire to the other wire directly through this small resistance rather than going through the appliance, okay? It asks you to calculate the rise of the temperature of the surrounding materials, which is only 2 grams. And assuming the specific heat capacity of the material is 0.2 calories per gram times degrees Celsius. And when that happens, it takes 0.05 seconds for the circuit breaker to interrupt the current. So is this likely to be damaging? So that means or in the other word, what would be the temperature rise in that small time period? So if the temperature rise up too large, then it could be damaging. Okay. So this problem, it's kind of integrated concepts. So you need to know like the power, all right? Electric power here. So P, you can calculate it. You can use one of those three expressions. P equals to V squared over R, okay? And then it tells you T is equal to 0.05 seconds. Now the material has a mass of 2.00, that's in grams. So you want to make appropriate conversion to SI unit. So times 10 to the minus 3. It says the specific heat capacity. That is 0.2 calories per grams degree Celsius. All right. So you probably want to convert this into joules per kilogram degree Celsius. 1 calorie is 4.86 joules there. All right. So in another word, what will be the change in temperature here? That's what you're looking for. So remember that the power being consumed by the resistor is pretty much becomes the heat. Okay, so then you can connect the two here. So heat then it's equal to P times T. All right. And then heat is given to the surrounding materials. So you can calculate the temperature change from this equation that we learned from specific heat. All right. So let's take a look here. So we can calculate, well, actually, I think we can start from here to calculate power first. So you are given voltage, you are given resistance. So you might figure out that this is the equation you want to use for power. Okay, so V square over R. All right, and then times T will give you Q. So let me just start from Q equals to P will be V square over R times T. Okay, so 120 volts squared divided by 0.500 ohms times T times the 0.05 second. Okay, that will give you 1440 joules of heat being generated in that time period. All right, and then we can use that to solve for delta T from here. So delta T, the increase in temperature of the material will be equal to Q divided by MC from there. So then it's 1440 joules divided by the mass as 2 grams. As I said, you can convert into kilogram appropriately, or you can, if you take a look on the specific capacity given, this is in grams, okay? So in this case, you actually do not necessarily have to convert that, okay? So just use 2 grams here, and then this is grams times degrees Celsius, so that and that will cancel out, okay? But this is 0.200 calories. You do want to convert calories into joules there. So 1 calorie is 4.186 joules there. All right. Then it will give you, if you put everything into a calculator correctly, this will give you 860 degrees in Celsius. All right. So that's a rather large increase in temperature. Okay. So it could be damaging in this case. All right. Any questions you guys might have? All right. The last section here talks about the nerve conduction system. So basically, the signals that's going through our body, it's pretty much electric signals. Okay, so you guys can read this section. So I don't think I'm going to go into too much details of this. Okay. All right. So then that should do it for this chapter. All right. We'll stop here for today then.